All right, hello everyone. Welcome to Limpid Scholars Tutorial on another episode of our chemistry class. Please, if you have not subscribed to our channel, please do that now because you'll be missing a lot of things. Because this time around, we'll be dropping back to back class teachings on chemistry, physics, or either biology class. Today, we'll be looking at gas laws, ideal gas laws, and its related problem. Now, we'll be starting with ideal gas. Ideal gas. Ideal gas. Ideal gas means any gas that perfectly obeys the law of Boyce and Charles. Take a look at it. I said Boyce law and Charles law. Ideal gas perfectly obeys the law of Boyce and Charles law. Now, what is Boyce law? Boyce law states that the volume of a given mass of gas is inversely proportional to its pressure, provided that the temperature or its molecules remains constant. I will not be writing now because of space. Now, it said Boyce law is what? The volume of a given mass of gas that is inversely, in your mathematics, you should all understand inversely by now. Inversely proportional to its pressure, provided that the temperature or its molecule or moles remains constant. So it is not only temperature that is constant, even the moles. Now, what about Charles law? Charles law states that the volume of a given mass of gas is directly proportional to its temperature, provided that pressure and its moles are constant. Volume directly proportional to its temperature, provided that pressure, moles are constant. Now we have established the fact that ideal gas are any type of gas that perfectly obeys Boyce law and Charles law. Unfortunately, there are no sort of gas that behaves like an ideal gas. There is no any gas that is ideal. Now, there are some properties of ideal gas. Ideal gas. When a gas is ideal, there are some properties in which it exhibits. Ideal gas are gas that behave under these two principles. One is low pressure and high temperature. High temperature. I hope we're getting that. A gas is said to be ideal when it behaves under low pressure and high temperature. Don't worry, we're still coming back to this and we'll still deliberate and solve more questions, JAMB sample questions under that. Now, low pressure and high temperature. A gas starts to deviate from being an ideal gas, meaning a gas starts to deviate from its ideality when it starts acting under these two principles: high pressure and low temperature. Now, when a gas starts behaving like this, it is no longer said to be an ideal gas. It is now called rare gas. Rare gas. They are referred to as rare gas. Now, fortunately, we have gases that behave like rare gases. Example of rare gases are, we have your carbon dioxide, we have your oxygen, we have your nitrogen, and so on and so forth. These gases are rare gas, because the ideal gas are said to deviate from its ideality, which is supposed to operate under low pressure and high temperature. I hope you get that. I hope you understand that. Ideal gas exhibit this property under low pressure, high temperature. But when it deviates from its ideality, it now operates or exhibits this it exhibits this principle: high pressure and low temperature. So I hope you get that. Now there are some factors that influences the ideality of a gas. Let me write it here. Factors that influences the ideality of a gas. Number one factor is low energy, which we refer to as less energy. You can call it what? Less energy. Because of the lower amount of energy, they tend to what? Deviate from their ideality. And the second factor is the high intermolecular force. Intermolecular, I'm writing like this: intermolecular force. These are factors that influences the ideality of a gas. But ideal gas operate on a normal circumference or a normal circumstance. They operate under low pressure and high temperature. Now, let's go back to ideal gas. Now, we're talking about ideal gas. Now, let's look at ideal gas law. Ideal gas law. Now, ideal gas law are gotten or derived from three laws. Ideal gas are gas that perfectly obeys both Boyle's and Chau's law. But ideal gas law is derived from three laws. The first law, definitely we must have Boyle's and Chau's law. Now, what will come to your mind is what is the third law. Number one is Boyle's law. Boyle's law. Two, we have Chau's law. And three, we have the Avogadro's law. Avogadro's law. Now, I have stated the Boyle's law. I have stated the Chau's law. Now, what is Avogadro's law? You know it has a number and it is constant, right? Avogadro's law states that equal volume of all gases at the same temperature and pressure contains the same number of molecules. That's why we have them here. So meaning Avogadro's law, equal volume of all gases at what? Constant temperature and pressure. Constant. Hope we are saying this. Equal volume of what? Equal volume of gases and what? Molecules at what? Constant temperature and pressure. That is Avogadro's law. Its number is Avogadro's number equals to 6.02 times 10 raised to power 23. That is the number. We are going to make use of this. That is why you must subscribe to our YouTube channel if you have not done that. Hit the subscribe button now, because we are going to be bringing up some questions under stoichiometry, more concept. You are going to be needing this Avogadro's number very well. We are going to be using this very, very well, doing solving questions under your more concepts, under stoichiometry and the rest. But our main focus today is under gas laws. Now we're talking about the Boyle's law, the Chau's law, and the Avogadro's law, which from them we derive the ideal gas equation. Now let's go on to the derivation of ideal gas. Let's derive the ideal gas. Let me rub this off, please. I'm going to rub this off. I hope you have taken note of that. Please, I believe everyone watching this channel should get their books and their pen and jot down every information. I might not be able to write down everything on the board. So that is why you need to get your book and your pen. Now, derivation of ideal gas. Derivation of ideal gas. Ideal gas law. Yeah. Now, I said ideal gas law is derived from three laws: Boyce, Charles, and what? Avogadro's law. Avogadro's law. Right? We have Boyce law as we said the volume of a given mass of gas is inversely proportional, right? So we have it as P1 V1, P2 V2, right? So Charles law is okay, let me write it. Volume of a given mass of gas inversely proportional to pressure. So temperature and moles are constants. So Charles law, volume of a given mass of gas is directly proportional to temperature. Pressure and moles are constants. So I'm repeating this again. Avogadro's law, volume and number of moles are equal. Temperature and pressure are constants. And temperature, pressure are constants, not moles, are constants. Now let's derive this. What is common among this formula is volume. So volume is common. Then we have pressure, inversely proportional. We have temperature, and we have number of moles. Right? Now, V will be equals to Tn over P. Right? Now, we have V equals to Ktn over P. Now, in ideal gas law, K is what we call the proportionality constant. This is constant, right? But in ideal gas law, we call it proportionality constant. And it is represented as R. We use R to represent it, proportionality constant. It has a figure, it has a value. I've not gotten there. We'll get there now. So we have V equals to RTN over P. Let's cross multiply. Then we have what? PV equals to, we are rearranging this figure. Rearrange them. Let's rearrange. PV equals to nRT. We have PV equals to nRT. Note that R is constant. So the value of R is equal to 0.082 mole per dm cube per Kelvin, right? So this is constant. Your R is constant, and R is called proportionality constant. Please take note of that. Proportionality constant. So we have gotten to how ideal gas law was derived. So this is the ideal gas law, and this is the figure. By now, as an UTME candidate preparing for UTME next year 2026, you should know this, even if you are not given at all. At times, JAMB might not give you this in the question. So by now, you should cram this, get it into your brain, that proportionality constant in ideal gas law R is 0.082. Please take note of that, 0.082. Now, let's go into questions. Let's solve questions. Like I promised, we're going to solve questions under gas law, ideal gas law. And since we have talked about Boyce law, Charles law, before we go into question, let me just bring our attention to this. Let me draw our attention to this general gas equation. This is what we call general gas equation. So we're talking about gas law. Let's treat this. General gas equation is the combination of Boyce law, Charles law, and even the pressure law. Are you getting it? So it is given as P1 V1 over T1 equals to P2 V2 over T2. So general gas equation is the combination of these laws. That's the combination of Boyce law and Charles law. Yes, rather. Sorry for the mistake. So general gas equation is the combination of Boyle's law and Charles law. So we have it as this: P1 V1 equals to P2 V2 over what? T1 over T2. So do we get that now? Now let's go into questions. Let's solve questions now. Questions. This is UTME questions. Let me write it boldly. UTME question. Questions. So we'll be solving 10 questions under this topic. If you don't know how to calculate, you can get your calculator now and get your notes. So the question will be displayed on the screen. I don't want to write it here. So it will be displayed on the screen. So let me read out the question as we get it. Oh, sorry. Sorry about this. So let me read out the question. Question 1, look at it on the screen. If the pressure of 200 centimeter cube of a gas is halved at constant temperature, what will be its new volume? Now, from the question, let's analyze this question. If the pressure of 200 centimeter cube, volume is measured in centimeter cube, pressure is measured in ATM, atmospheric pressure, or millimeter mercury. Anywhere you see this, please take note that this is the measurement for what? Pressure. Why? Temperature is measured in Kelvin. Most questions, whether UTME or in your WAEC, you will be given temperature in degrees Celsius. So you have to convert it from degrees Celsius to what? Kelvin, because that is the acceptable unit of measurement. But if you are given it in Kelvin, just leave it. So how do you now convert from degrees Celsius to Kelvin? Is whatever value you are given in Celsius, whether 12 degrees Celsius, you add 273 to it. It will give you your number in Kelvin. Do you get that? So I've established that. So now let's continue from our question. It says V, the volume, if the pressure of 200 centimeter cube, that is, volume is 200 centimeter cube, of a gas is halved, meaning P2 is equal to half of what? P1. What will be its new volume at constant temperature? Temperature is what? Constant. What will be its new volume? That's V2 is unknown. Now let me tell you something. Some students see this question, and that's why I'm telling you that at the end of this class, if you fail any question under gas law or ideal gas law, you have yourself to blame. You just have yourself to blame. Just follow me very, very closely. Now, how do you know, or some students might ask themselves, how do I know what law to use? Either Boyle's law or Charles law. That is why you must know their law. Boyle's law states that a volume of a given mass of gas is inversely proportional to the pressure, provided that the temperature is constant. Now, if you read the question, at the end of the question says is halved at constant temperature, meaning this law we're going to use is Boyle's law. And Boyle's law is P1 V1 equals to P2 V2. Are you getting something? Are you getting something at all? Now, P1 is already half of P1. So P2 is half of the what? P1. That's how we get the value of P2. Now let's solve. Let's put this. We've got it now. P1 V1 equals to P2 V2. Your P1 is just P1, right? It says half. So when you have half here, you have half there too. So we have P1. So when we do it, we got to eliminate it. So we have multiplied by 200 centimeter cube equals to P2 is half of P1, right? So it's half. So multiply by volume, we don't know the volume, right? This one we cancel this, right? So we are left with what? This is P. We said our P1 is half of P1 is half already. So P2 is half of the what? P1. So half P2, right? I hope there's no mistake. Hope there's no mistake, right? So we have it as this one P1 are given times 200 centimeter cube equals to half of P2 multiplied by the volume. This volume, we don't know it yet, right? So what we do now is P1 we cancel. I said P2 is half of P1 rather, sorry. So P1 we cancel P1. We're left with 200 centimeter cube equals to what? V2 over 2. Multiply both sides by 2. We multiply both sides by 2 to eliminate what? 2. Or we can just cross multiply instead of saving time. So V2 will be equals to 200 centimeter cube multiplied by 2. V2 equals to 400 centimeter cube. That is the value of your what? V, of your new V. Now, let me tell you something, guys. Because of UTME sake, do you know I can solve this question within 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Considering other factors, right? Maybe I might be slow or something, or because of calculator. I can solve this question within 10 seconds. This question might have taken us maybe probably 1 minute. I can solve this question within 10 seconds as a UTME standard. Now, the question is not this principle. Sorry. Not this principle, guys. That whenever a pressure is being halved or reduced, the volume will be doubled. You didn't get that. When pressure reduces, volume increases. That is Boyle's law. That is why it's inversely proportional. So as pressure is increasing, volume is decreasing. As volume is increasing, pressure is reducing or decreasing. Now, the question says the pressure was halved, so it was reduced to half, meaning your volume will be doubled. How do you double your volume? You multiply the volume by 2. So from the question, you don't even need to calculate this in UTME question because there's no time. So when you're given the volume, just multiply your volume by 2. You get 400 centimeter cube. Check it out. Now, let's take an example. Probably somebody might be saying, maybe it's this question or something like that. Let's take, for example, another question. Let's take this question. Let's take this question. Let's take this question. Let me look for a similar question that applies to this. Look for a similar question. We need question like this. So I'm coming, guys. I'm coming. Calculate the temperature. All right, I think I'll find the question. A gas occupies a volume of 150 cm cube at a pressure of 60 millimeter mercury. If the pressure is reduced to 300 millimeter mercury, meaning the pressure was 600 millimeter mercury, now it was reduced, right? Probably it might be 400 or anything, but it was reduced to what? 3 millimeter mercury. At constant temperature, it is still under Boyle's law. Boyle's law, temperature and the moles are constant. Find the new volume. Do you need to solve this question? Do you need to start writing down? Whereby you are given how many hours to solve how many questions in UTM 180 questions. Now, what is the volume? The volume is what? 150. And they said the pressure was reduced. What do? 150 multiplied by 2 will give you what? Will give you 300 cm cube. So our new volume is 300. You don't need to be solving all this. It is principle that you must apply. That is why some persons are given luxurious time, but they still not finish because you waste time on questions that are not supposed to be really solved. Do you get that? So we have tackled that. That's 2 questions. That's 2 questions. That's question 2. Yeah, we have solved. If you apply the same formula, you will still get it 300 centimeter cube. Now let's look at another question very quickly. Another question. A sample of gas, this is question 3. A sample of gas exerts a pressure of 82 atmospheric pressure, 82 atm, So that means pressure equals to 82 atm when confined in a 2.93 dm cube volume, 2.93 dm cube container at temperature of 20 degrees Celsius. The number of moles of the gas in the sample is unknown. I'm not given the number of moles. Now, I forgot. In ideal gas equation, the volume is always in dm cube. That's why we have it as 0.082 mole per dm cube that, right? So you know that. So remember that ideal gas equation is PV equals to nRT, and your temperature is always in Kelvin. That's why you see at the end of the formula we have Kelvin. So therefore, convert T to Kelvin. So 20 degrees Celsius to Kelvin will be what? Kelvin will be equals to what? 20 degrees Celsius plus 2273. So let me calculate this. Just open your calculator and do this. So we have it as 20 plus 273 will give us what? 293 Kelvin. Don't go and do I to know. Punch that calculator on your screen and calculate this so that you get the right value. Now that is it. So we have balanced that for Kelvin, for temperature, we have volume, and we have pressure. Now let's put it into the formula. PV equals to nRT. Then we have 82 multiply. Oh yes, we are not given R. I'm not sure they put the value of R here. You see, the value of R is not given. But because we have understand from the beginning that 0.082 is the value for R, proportionality constant. Therefore, we have no problem. 2.93 equals to moles, we don't know it, times 0.082 multiplied by the temperature 293. Don't go and use this one, no, it has already been converted. This is the exact one you're going to use. Now, let's multiply. Let's do calculation. 82, take your figure very well, please. Multiply by 2.93. Multiply by 2.93. Don't go write 293. Oh. That's why you need to read your question very well to give you another figure entirely. So it will give us 240.26. Now 0.082 multiplied by 293 to give us 24.026. Now let's collect like terms and divide both sides. 2.26 divided by 24.026, right? So 240.26 divided by 24.026. What will be left with? The number of moles will be what? 10 moles. And is that part of the options? We have 10 moles or 1.0 moles, 0.82. So we have 10 moles. So 20 points, let me see, 240.26 divided by 0.26. So we have 10 moles. Some example, probably the way they do their conversion, you might have it as 1.0. So you know you're closer to the answer. So you choose 1.0, right? So let's move on. I think this is the third question. Now, question 4. We're going to question 4. Now, let's take question 4 now. Let's take question 4. The pressure exerted by a sample of gas confined in 5.86 dm cube. 5.86, that is volume, 5.86 dm cube container at temperature of 20 degrees Celsius is what? Pressure is 4.1 atm. What is the number of moles again? Listen. The pressure exerted by a sample of gas confined in 5.86 dm cube container at 20 degrees Celsius is 4.1 atm. What is the number of moles of gas in the sample? Now here we're given R as 0.082. Yeah, JAMB was nice then. That's why they put this. But if they're not nice, they'll remove it. So you have to know that. So PV equals to nRT, right? We don't need to talk about that. So we have 4.1 multiplied by 5.86 equals to number of moles, we don't know it, multiplied by 0.82, that's 0.082, right? 0.082 multiplied by, convert 20 degrees Celsius. Imagine, remember what converted it that time. So put it as 293. Therefore, what do we have? What is our answer? Let's calculate. 4.1 multiplied by 5.86, we have 24.026. I think we're going to get the same answer similar to that question we solved. 82 multiplied by 293, 24.026. So times n equals to 24.026 over 24.026. Some people will still want to calculate. Is it not 1? It is 1.0 moles. That is the number of moles, right? Is it not getting interesting? Question 5 now. By the end of this class, you should not fail any question that comes under this topic. It should be a bonus mark to you. Like I've told us, there are some questions that we need to solve. There's some questions that we just calculate and then give the answer. Now let's continue. Question 5. A gas occupying an initial volume of 2 dm cube, that is volume, initial volume, meaning V1 equals to 2 dm cube, is heated and allowed to expand to 6 dm cube, equal to 6 dm cube, at constant pressure. Pressure is constant. The ratio of the initial absolute temperature to the final absolute temperature is what? Meaning T1 ratio T2 is what? That's what we're going to find. This tells us that this equation will be solved using Charles' law because pressure is already constant. Now, if I ask to find the ratio of the initial temperature and the final temperature, so we have it like this. Since V1 over T1 equals to V2 over T2, and then we have the temperature here, which are the ratio, so we can have it like this. V1 is what? 2 over what? 6. Yes, you can leave your answer like that, since they are asking you to find the ratio. But assuming you are asking you to find the volume, and probably maybe the volume is in cm cube, you are going to convert these guys from dm cube to cm cube. But since they are just asking for the ratios of the temperature, so you can leave it like this. So 2 here 1, 2 here 3. Therefore, the ratio 1 of the initial temperature to the final absolute temperature is 1:3. And the option is option B. These are the options there. Option A, 3:1. B, 1:3. C, 2:1. D, 1:2. Some people don't get it twisted. Don't put V2 for V1 and say 6 over 2, 2 here 1, 2 here 3. I got it now, 3:1. You will fail it woefully. You will fail it woefully. Obey the instruction. Follow the instruction strictly. If we have V1, this is it. We have it T1, so we're looking for the temperature at V1 over what? T over what? V2. So V1 2, V2 6. That's the ratio. So very quickly, guys, let's move on to question 6. Question 6. A given mass of gas occupies a volume of 300 centimeter cube. 300 cm cube. Volume. When you hear cm cube, dm cube, you know that is volume. At 900 millimeter mercury pressure, this time around they did not use ATM. They use mmHg. that is still pressure, equals to 900 millimeter mercury. Calculate the volume occupied by the same gas, that is your V2, we don't know it, at pressure of 750 millimeter mercury if the temperature is constant. We don't know temperature, but we know what? We don't know the temperature, right? Temperature is constant, rather. We don't know the volume. So temperature constant. Now let's solve. Temperature is constant. That tells you that we are using what? Boyle's law. So P1 over V1 equals to P2 V2. So we have our P1 as 900 times V1 300 equals to P2. Sorry? P2. This should be our P2. This should be our P2. Let's see the question. This should be our P2 rather. So P2 750 times V2. So I'll put this as our P2. Now let's calculate. This is my calculator. So use your calculator and let's calculate. 900 multiplied by 300 will give us 270,000 equals to 750 multiplied by V2. To find the value of V2, make it as the whole number, and then 270,000 divided by 750. I know we know this. It's a simple mathematics. Divided by 750, we have it as what? 360 cm cube. That is our final answer. So let me read the options. We have A 360 cm cube, B 380 cm cube, C 300 cm cube, D 320 cm cube. So our answer is B. A 360 cm cube. Now, let's solve question. Now, moving on to question 7. Moving on to question 7. I know even by now, we can solve any question under this topic. But let's just continue because I'm enjoying it. So, let's continue. Question 7. A gas has a volume of 300 centimeter cube. Volume 300 centimeter cube. That's the first volume. So we give it as your V1. Let's continue. At 27 degrees Celsius, T1 equals to 27 degrees Celsius. Find its volume at V2 unknown. T2 equals to 127 degrees Celsius. If the pressure is constant, what are we going to use this? I'm asking you. What are we going to use this? We are using Charles' law here. As says V1 over T1 equals to V2 over T2. Provided that pressure remains and moles remains constant. So now we are going to convert our temperature to Kelvin. So we convert it by saying 27 plus 273 and what? 127 plus 273. Temperature 1, temperature 2. Now let's calculate again. 27 plus 273, we have it as 300 Kelvin. 127 plus 273, we have it as 400 Kelvin. Now let's insert our figures. 300 centimeter cube over T1 is what? 300 K equals to V2 is unknown over 400, right? For me, 227 plus 273. That's 127 plus 273. That's 400 over 400. Cross multiply. V2 multiplied by 300 equals to 400 multiplied by 300. V2 equals to 400 multiplied by 300 over 300. So this will give us our answer as what? 400, because 300 can actually cancel 300. So our V2 equals to 400 centimeter cube. So the options: A is what? 350, B 400 centimeter cube, C 450 centimeter cube, D 500 centimeter cube. So our answer is B, 400 centimeter cube. Now question 8. We're almost getting to the final lap. Question 8 says the pressure of 2 moles of an ideal gas. So they've stated it here. You should already know that it's ideal gas. Question 8. Ideal gas equals to PV equals to nRT. Is a brighter marker. nRT, right? So occupying a volume. So they said the moles is what? 2 moles of an ideal gas occupying a volume 10 dm cube at a temperature of 300 K is close to, so they asked us to find the pressure unknown. They gave us R as our 0.082. They're giving us R. Thank you for them for giving us R. So what do? Let's insert our figures into this. Our temperature is already in Kelvin, so we don't need to convert. Now we have P multiplied by volume is 10 equals to our mole is 2 multiplied by 0.082 times 300. So P will be equals P times 10 equals to, let's multiply what we have at the product side. 2 times 0.082 times 300. We have it as 49.2. P will be equals to 49.2 over 10. This is coming over to this place. So let's divide it by 10. We have it as 4.92. P equals to 4.92 atm. Depending on your option, let me read out the option. Option A, 4.9 atm. B, 6.2 atm. C, 7.4 atm. D, 9.8 atm. I hope this is balanced. So let's cross check again. 2 times 0.082 times 300. 49.2. So 49.2 divided by 10, which is our point. We have 4.92. So from the question here, we have 4.9, 6.2, 0.4, 9.8. So 4.9 is our equation. Assuming this is up to 5, we can round it off. And then we'll have 0 here, and this one will give us 5, right? So 4.92, depending on the significant figure or decimal point place they rounded it up to. So question 9, the last question before the final question. Question 9 says a gas occupies a volume of 250. Volume of 250, that is volume 1. At pressure of 4 atm, pressure 1, 4 atm. What will be its volume? The new volume is unknown. When the pressure is increased, pressure is increased to what? The pressure is increased to 10 atm. The temperature remains what? Constant. Like I said, when they say the pressure is increasing. So when pressure is increasing, volume is decreasing. Don't worry. Option A, 50 cm cube. Option B, 100 cm cube. Option C, 125 cm cube. Option D, 625 cm cube. I'm not going to solve this question. They say the pressure is increasing. So when pressure is increasing, volume is decreasing. Divide your volume 250 divided by 2, you have 125 cm cube. That's your answer. No stress. UTME brace. Straight up. But when we calculate it, let's calculate it and see. Let's calculate it. Somebody might be doubting. So let's calculate it now. So temperature is constant. We have P1 V1 equals to P2 V2. Your pressure 1 is 4 multiplied by your 250 equals to P2 is 10 multiplied by V2. So let's have it. Let's calculate now. 4 times 250, we have 1000 equals to 10 times V2. Coming? 10 times V2. 4 multiplied by 250. Let me see. 250 cm cube. 250 cm cube, right? 10. 10. Okay, 1000. So cross multiply. V2 equals to 1000 divided by 10. There cancel 0. V2 is equals to 100. Okay. Sorry, I made a mistake. That principle applies to when the pressure is reduced, your volume will increase. Sorry about that. Sorry for that mistake. Sorry. So your answer is not 125 cm cube. Your answer is not 125 cm cube. Your answer is 100 cm cube because we have an increase in pressure. We have an increase in pressure that is what? 10 atm. And because they are not really a factor, like because when you have 4, 10, 2 here, 2 here, 5, 2 over 5, right? So let's have it like this. It's not doubled. It's not doubled. That's why it's not doubled. So we have our volume. That's the V2 as what? 100 centimeter cube. That's our volume for. That's the volume for that's the volume. That's the second volume. That's the V2. Now, lastly, let's take a look at the last question. Question 10. Question 10 says, a fixed mass of gas has a volume of 500. V1 equals to 500 cm cube. At temperature of 27 degrees Celsius and a pressure of 760. Calculate the volume V1 at temperature T2 equals to 127 degree. If the pressure is reduced to what? 380 millimeter mercury. 280 millimeter mercury. So now we have V1, T1, P1, V1, and V2. We have V2, T2, P2, right? And I said general gas equation is the one that combines the two laws together. So we have our general gas equation. Remember that our general gas equation we said is what? P1 V1 T1 P1 V1 over T1 equals to P2 V2 over T2. So we have it as P1 is 760 multiplied by V1 500 over our temperature. We're going to convert it 27 plus 273 for T1. T2 equals to 127 plus 273. Right? Yeah, I think we're correct about that. So let's calculate this. Let's calculate this very fast. Oh, sorry. So let's calculate this. T1 27 plus 273. We have it as 300. So let's just put it 300 equals to temperature is 127 plus 273. I have it as 400. So we have 400. Our P2 is what? 380 multiplied by the V2. Now let's continue. We multiply. We have it as V2 equals to 380 multiplied by 300 equals to 760 multiplied by 500 multiplied by 400. Hope you are getting this very clear. Is this clear? So V2, okay, sorry, this is multiply V2. So let's multiply 380 multiplied by 300. We have it as V2 times 11400 equals to 760 multiplied by 500 multiplied by 400. So we have a large number 152,000,000. Now, to get the value of V2, let's send this to that side so it becomes division. That's your indices 152,000,000 divided by 114,000,000 0, right? 0. So let's divide it. So you make use of your calculator. 152,000,000. Hope you are calculating it. Divided by 114,000. Right? So the value of our volume, with hope there's no mistake. P2. Where's our P2? 760. Right? 760, yes. This is 760. Our volume is 500, right? 500. Volume 500. Sorry, we meant to multiply this. This is a mistake. This should be under this. Sorry, we meant to multiply it. It should be under that. So we have 760 as our P1. That's the first pressure. Sorry, that's the first pressure. That's the first pressure. So 760 multiplied by 500 over 300 equals to 380 multiplied by V2 over 400. So let's cross multiply. We have it as V2 times 380 times 300 equals to 760 multiplied by 500 multiplied by 400. So 380 multiplied by 300, have it 114. Okay, that's the same answer. V2. So equals to, let's multiply this quickly. Sorry, let's multiply 760. Let's multiply 760 by 500. 760 multiplied by 500 multiplied by 400. So we have it as 152,000,000. So this is it. So what do you do now? Let's collect like terms. Right? So collect like terms. So V2 will be equals to 152,000,000 divided by 114,000. So let's divide it. When you divide it, we'll have V2 as equals to 1333.33, right? Cm cube. So our final volume will be equals to 1333 cm cube. That's our final volume. So I hope at the end of this class today, this brings us to the end of the class, right? So I hope we have learned a lot about Boyle's law, Charles' law, Avogadro's law, the general gas equation, and the ideal gas equation. There are still numerous examples, but with these few examples, I know you can do justice to any question under this topic. Please click, share our YouTube channel, and subscribe to that subscription button to get notified on any tutorial class on more topics under chemistry, physics, or biology. Thank you guys for watching. Thank you.